Imagine discovering a machine that could generate electricity day and night, survive violent storms, operate almost silently, and help power a home throughout the year. A machine based on a mathematical principle that is more than 2,000 years old. A machine that engineers have tested, homeowners have installed, and researchers have studied. And yet, despite all of that, most people have never heard of it. Not because it failed, not because it was unsafe, not because it didn't work, but because it arrived in a world that had already chosen a different path. This is the story of a wind turbine unlike any other. A turbine inspired by an invention from the ancient world. A turbine that challenges many of the assumptions we have about residential wind power. And a turbine that raises a fascinating question. If this technology is as effective as its supporters claim, why isn't it everywhere? To answer that question, we need to start with a problem that affects millions of homes around the world. Energy. For decades, homeowners have searched for ways to reduce their dependence on utility companies. Every year, electricity prices climb a little higher. Every year, concerns about grid reliability become more common. And every year, more people begin asking the same question. What would it take to generate most of my own power? Over the last 20 years, solar energy has become the most popular answer. Rooftops once covered only with shingles are now covered with photovoltaic panels. Entire neighborhoods have embraced solar technology. Battery systems continue to improve. And for many homeowners, the dream of partial energy independence has become a reality. But there is one weakness that solar power cannot escape. The sun does not shine at night. It produces less energy during storms. It struggles during long periods of cloud cover. And in many regions, winter dramatically reduces production just when energy demand begins to rise. This is where wind should enter the picture. After all, wind power offers something solar cannot. It can generate electricity 24 hours a day. It often becomes stronger during the colder months of the year. And in many climates, it naturally complements solar energy. When one source weakens, the other often grows stronger. On paper, the combination seems almost perfect. Yet there is a strange contradiction. Drive through almost any city or suburb and you will see solar panels. You will see batteries. You might even see electric vehicles. What you probably will not see are residential wind turbines. At least not many of them. That absence is not an accident. The truth is that traditional small-scale wind turbines have struggled for decades with a problem that most people never think about. The problem is not generating electricity. The problem is where people live. Large commercial wind farms are usually built in open spaces. Flat plains, mountain passes, offshore locations, places where wind flows smoothly and consistently. But residential environments are completely different. Cities and suburbs are chaotic from an aerodynamic perspective. Buildings interrupt airflow. Trees create turbulence. Roofs redirect wind in unpredictable directions. Instead of moving smoothly, air twists, swirls, accelerates, and changes direction constantly. For conventional wind turbines, these conditions can be disastrous. Many small turbines are designed around the same aerodynamic principles that allow airplanes to fly. They require relatively clean airflow. They prefer stable wind direction. And they perform best when conditions remain predictable. Unfortunately, urban wind is anything but predictable. As a result, many residential turbines never come close to their advertised performance. Some generate disappointing amounts of electricity. Others become noisy. Some require frequent maintenance. And many homeowners eventually decide that the effort simply is not worth the reward. For years, this problem seemed unavoidable. Engineers refined blade designs. Manufacturers improved generators. Companies introduced new materials and new control systems. Back to an invention created long before electricity existed. When turned, the spiral lifts water upward with remarkable efficiency. Simple. But in all that time, almost nobody asks a particular question. For more than 2,000 years, the Archimedes screw remained a machine designed to move water. Then, in the early 21st century, a Dutch inventor named Marinus Meermat looked at the ancient design and saw something different. He wondered whether the principle could be reversed. Instead of using mechanical energy to move a fluid, what if a moving fluid could generate mechanical energy? At first glance, the idea sounds simple. In reality, it required an entirely new approach to wind turbine design. Traditional wind turbines rely on long, narrow blades that function much like aircraft wings. When wind passes over these blades, pressure differences are created, generating lift and causing the rotor to spin. This design works exceptionally well in large open spaces where airflow is smooth and predictable. That is why commercial wind farms are usually built in wide open plains, mountain corridors, and offshore environments. But residential settings present a completely different challenge. Near homes and buildings, wind rarely behaves in a predictable manner. Airflow collides with rooftops. It bounces off walls. It changes direction constantly. It speeds up and slows down within seconds. For conventional turbines, these conditions create inefficiency. The rotor often struggles to remain aligned with the wind. Mechanical systems must constantly adjust orientation. Vibrations increase. Noise levels rise. And energy production falls. Marinus Mirmet believed the answer was not to improve the traditional turbine. The answer was to rethink the geometry entirely. Drawing inspiration from the Archimedes screw, he developed a rotor that looked unlike anything most people had ever seen. Instead of straight blades, the design featured a flowing spiral shape wrapped around a central axis. Many people compared it to a seashell. Others said it resembled a sculpture more than a machine. But behind its unusual appearance was a carefully engineered aerodynamic structure. As wind enters the front of the spiral, the curved surfaces guide and compress the airflow through the rotor. The air changes direction as it moves through the turbine. During this process, energy is extracted from the wind and converted into rotational motion. The result is a turbine that behaves very differently from conventional designs. One of its most important advantages is self-orientation. Most traditional turbines require mechanical systems to keep the rotor facing the wind. The spiral design naturally tends to position itself in the most favorable direction. This reduces complexity and decreases wear on moving parts. It also allows the turbine to respond more effectively to changing wind conditions. Another advantage is its ability to operate in turbulent airflow. This is critical for residential installations. A conventional turbine may lose significant efficiency when wind approaches from an angle. The spiral turbine remains effective even when airflow is inconsistent or partially misaligned. That characteristic alone makes it far more suitable for urban and suburban environments. Then there is the issue of startup speed. Every wind turbine has what engineers call a cut in speed. This is the minimum wind speed required before the turbine begins producing useful electricity. Many conventional residential turbines need relatively strong winds before meaningful generation begins. The spiral design is capable of starting and producing power at much lower wind speeds. That means it can generate electricity during conditions when many competing systems remain completely inactive. Over the course of a year, those additional operating hours can make a substantial difference. But perhaps the most striking aspect of the design is its behavior under real-world conditions. Many technologies perform impressively in laboratory environments. The real test comes outdoors. Rain, storms, temperature fluctuations, changing wind directions. Years of continuous operation. That is where many promising inventions fail. Yet the Archimedes-inspired turbine continued attracting attention because it demonstrated impressive stability in precisely those conditions. Researchers studying the design observed that it remained remarkably consistent across a wide range of operating environments. It could start in gentle breezes. It remained functional in turbulent air. And it tolerated changing wind directions without the constant adjustments required by many traditional systems. Noise was another area where the turbine stood out. One of the most common complaints surrounding residential wind energy has always been sound. Fast-moving blades create aerodynamic noise. Mechanical systems generate vibration. Over time, these factors can become a source of frustration for homeowners and neighbors alike. The spiral turbine approached the problem differently. Its rotational speed is generally lower. Its aerodynamic behavior is smoother, and the resulting sound levels are significantly reduced. For many homeowners, that difference alone can determine whether a turbine is practical for residential use. There is also the question of wildlife. Conventional wind turbines have long faced criticism regarding bird and bat collisions. Although the issue is often exaggerated in public discussions, it remains a genuine concern in certain locations. The spiral turbine offers a potential advantage here as well. Its shape is highly visible. Its movement is slower, and its structure appears more recognizable to wildlife than rapidly spinning blade tips. Supporters of the technology frequently point to this as one of its most attractive characteristics. By this point, the design seems almost too good to be true. It handles turbulent wind. It operates quietly. It starts at lower wind speeds. It appears safer for wildlife. And it was inspired by a principle that has already proven itself over 2,000 years of engineering history. Which brings us to the most important question of all. If the technology performs so well, why haven't spiral wind turbines become the standard choice for homeowners around the world? The answer has very little to do with physics, and almost everything to do with economics. The answer has very little to do with whether the technology works. In fact, that is what makes this story so interesting. Many technologies fail because they are poorly designed. Others fail because they are unreliable. Some fail because they solve a problem that nobody actually has. The Archimedes-inspired wind turbine suffers from none of those issues. Its biggest obstacles exist outside the engineering itself. To understand why, we need to look at the numbers. Because no matter how innovative a technology may be, adoption ultimately depends on economics. Most homeowners are not searching for fascinating engineering. They are searching for savings. And that changes everything. Imagine two homeowners standing side by side. Both want to reduce their electricity bills. Both have similar budgets. Both are interested in renewable energy. One is offered a solar installation. The other is offered a residential wind turbine. The first homeowner can easily find multiple installers. The permitting process is familiar. The technology is widely understood. The financing options are readily available. The second homeowner faces a very different experience. Finding qualified installers can be difficult. Permitting requirements may be unclear. Structural assessments may be required. And local regulations can vary dramatically from one community to another. Immediately, the path becomes more complicated. Even before discussing performance, complexity becomes a barrier. Then there is the issue of return on investment. A residential wind turbine can generate meaningful amounts of electricity, but the amount depends heavily on location. This is where many people make a critical mistake. They assume that wind behaves like sunlight. It does not. If two homes receive different amounts of sunlight, the difference in solar production may be noticeable. But with wind energy, small changes in average wind speed can create enormous differences in power output. That is because wind energy follows a cubic relationship. Double the wind speed and the available energy does not simply double. It increases dramatically. This means that location is everything. A turbine installed in a windy coastal environment may perform exceptionally well. The exact same turbine installed in a sheltered suburban neighborhood may generate only a fraction of that energy. The technology itself has not changed. The environment has. That reality explains why residential wind power has always been highly site-specific. Some locations are ideal. Others are not. For homeowners living near coastlines, open farmland, elevated terrain, or consistently windy regions, the economics can become surprisingly attractive. For everyone else, the financial case becomes more difficult. This is one reason solar expanded so rapidly, while residential wind remained a niche technology. Solar production is relatively predictable. Wind production is highly dependent on local conditions. The second major challenge involves infrastructure. When solar energy became popular, an entire industry emerged around it. Manufacturers, installers, inspectors, training programs, financing companies, maintenance services. The ecosystem matured. Today, in many regions, a homeowner can request a solar quote and have a functioning system installed within weeks. Residential wind never experienced the same level of development. As a result, many homeowners interested in small wind systems discover that the support network simply does not exist. Even when the technology itself is excellent, a lack of infrastructure slows adoption. Then there are regulatory challenges. Local governments often understand solar installations. Wind turbines are different. They involve moving structures. They may require additional engineering reviews. Some neighborhoods prohibit them entirely. Others impose restrictions based on height, appearance, or zoning requirements. In many cases, obtaining approval can take far longer than homeowners expect. Again, the issue is not the turbine. The issue is the environment surrounding the turbine. And this pattern appears throughout the history of technology. The best solution does not always become the dominant solution. Sometimes the winner is the technology supported by the strongest infrastructure, the strongest supply chain, the largest installer network, or the most favorable regulations. That does not mean the alternative is inferior. It simply means the market evolved differently. Yet despite all of these challenges, there are situations where the Archimedes-inspired turbine makes tremendous sense. Off-grid properties are a perfect example. For someone living far from existing power infrastructure, generating electricity independently can be far more valuable than achieving a rapid financial return. The ability to produce power day and night becomes extremely important. Remote cabins, agricultural properties, island communities, mountain homes. These environments often benefit greatly from hybrid renewable systems. A combination of solar, battery storage, and wind generation can create a level of energy independence that would have seemed impossible only a few decades ago. In these situations, the turbine becomes more than an investment. It becomes part of a resilient energy strategy. And resilience is becoming increasingly valuable. Around the world, power grids face growing pressure. Extreme weather events are becoming more common. Electricity demand continues to increase. A market built around solar had already gained momentum,